Okay, alright. So welcome to our next video on your transformer. So in this video, I'm going to show you the calculations involving all your transformers, alright, especially ideal transformer and then efficiency, and then how to calculate the power loss in electrical cable. Alright, I'm going to show you everything here. Okay, now first, transformer in the previous video already learned, they are used to increase or decrease the potential difference or the voltage. Alright, so technically they are transferring the power from the first circuit into the second circuit. Okay, now when we say ideal transformer, alright, meaning that no energy loss. Okay, that is the key thing. Alright, so meaning that your input power is completely converted into output power, meaning 100% converted. So in ideal transformer, the idea is like this. If here is, let's say, 10 watts, meaning the output power should also be 10 watts. This is what we call an ideal transformer. All right, but it's very rare for us to get like 100% efficiency. Right, normally the highest you can go is 99%. Okay, so in other words, your output power, right, normally will be a bit lesser than the input power. Okay, but it's okay. Let me show you the formula. All right, so ideal transformer, okay, meaning that your input power is equals to your output power right here. All right, so if you remember your power formula, the formula for your power is P equals to voltage times current. Okay, hence the formula for an ideal transformer. In other words, if you see ideal transformer in your question, meaning that you are going to apply this formula. Right, this is for ideal transformer. Okay, all right. So like we mentioned just now, right, efficiency of a transformer. Okay, not all powers will be converted into your output. Some will be released as heat. Okay, power loss here, right? If you look at the diagram here, power loss here, meaning that most of it will be released as heat. Okay, not most lah, some of it will be released as heat. All right, so in order to calculate the efficiency, the formula that we're using here is this one: output power divided by input times 100%. Or if you put like this, PO over PI times 100. Okay, and then we know, right, P is equal to VI, right? So I can actually also change it into like this: output, meaning secondary, divided by primary. Okay, VP VSIS divided by VP IP or IS. Okay, so meaning that your efficiency formula will be this one. All right, of course, what they call the power loss due to, you need to know the factors, or you need to know the factors and then how to reduce the factors. All right, so I just show you a quick go through lah. All right, type of power loss: eddy current. I did mention eddy current in the previous video in the transformer part. All right, so if I don't want eddy current, that's why we use laminated soft iron core. Okay, and then we use copper wire, low resistance. We don't use wire that has high resistance because this will cause the wire to heat up. All right. Okay, hysteresis is meaning the magnetization of the metal. Why we use soft iron core is because this one we can control the magnetism, meaning it can magnetize and demagnetize easily. That's why I use soft iron core. Okay, flux leakage is like this. Some transformer design is using the C-type transformer, meaning they take two different transformers and then they combine in the middle like this lah. Okay, so this middle part here, oops. Alright, this middle part here, okay, the joint here is very important. You cannot have any gaps in the joint. If there is a gap in the joint here, right, what happens is that your magnetic flux will leak out. Okay, so once your magnetic flux leaks out, right, meaning that the current or the induced current will be lesser, it will affect it. Okay, so flux leakage is when there is what we call the joint between the magnet, not the magnet, the metals are not proper, meaning they are not stick together. Okay, so I just go through very briefly on this. All right, so let's focus on the calculation. Okay, because a lot of calculations recall involving your transformer here. Okay, so let me just go to this question here. Okay, let's go through a simple one first. All right. Okay. All right. So a transformer is used to lower the supply voltage. Okay. Lower supply voltage meaning this is a step down. All right, from 240 to 3V. Okay, number of turns of primary coil is 1600. What is the number of turns on this secondary? Okay, so this formula Vp over Vs equals to like Np over Ns, right? Okay, so you just need to identify which is your primary, which is your secondary. So lower meaning step down, meaning your primary one, the voltage is higher lah. You already tell me. So this one is your, this is your Vp, and this is your Vs. Alright, and then they tell you the primary coil is 1600 turns. So we just put inside the formula Vp over Vs, okay, 1600 turns. Alright, Ns. Okay, if you divide this, alright, oh man, let me just quickly calculate this. 240 divided 3, you get 50, right? Okay, and then you just divide. So you get 20 turns. Okay, now another way for us to see this is by using the ratio. Remember, the formula is to allow us to see the ratio, right? So this is 3 and 240, right? So if 3 and 240, meaning the ratio is 1 to 80, meaning it's 80 times. Alright, 80 times lesser lah, since I'm going down. So meaning this one, you take 1600, if you divide 80, also you get 20 turns. Okay, alright, so that is how you use the formula. Okay, so the relationship of the ratio here is good for you, especially when you're doing objective. Okay, because objective you don't need to show the step, what you only want to find the correct answer. So yeah, you can use that. Alright, okay. Question 3 is a type of example where they want to know, or they want to see whether you understand. Okay, how does a transformer work? Like I said in the previous video, your transformer, the primary and secondary coil is not necessarily left and right. Okay, the transformer that we're using nowadays, right, the design is actually up and down. Okay, meaning the primary coil is at the top, secondary coil is at the top, and then the primary coil is at the bottom. Okay, it's something like this. Alright, so this one is your secondary coil, this one is your primary coil. Okay, this will allow you to have an efficiency more than around 99%. Okay, so remember, it's not left and right, not always left and right, it can be up, down also. Okay, so this one, right, they show you 4 different arrangements. Okay, what is required to be done? If I want to step up, okay, the voltage 4 times. So I highlight the 2 things here, step up and then 4 times. Step up meaning is from less to more turns. So less turns to more turns, and then the ratio must be 4. So if based on this diagram here, right, it's very obvious it's P and R. Okay, because here is 20 turns, here is 80 turns, so the ratio here is 4 times. Okay, so what needs to be done, right, meaning that I need to put my input at P and then my output at R. Okay, because I want it to be stepped up. So input here, output here. If I want it to be stepped down 4 times, then I just switch the position of my input and output. Okay, just a brief what they call introduction lah. Okay, question number 4, ideal transformer. So when I see ideal transformer, I know that I need to use the formula. Okay, the ideal transformer formula. Alright, used to supply power to 2 volts, 2 light bulbs at their rated power, blah blah blah. Okay, voltage of the electricity supply is 240. Alright, current in the primary coil. What is the current in the secondary coil? Okay, now in this case, alright, we need to look at the circuit here. Okay, so if I want to apply the formula here, VPIP, my primary voltage here is 240 because supply coming in. Alright, and then the current here is 0.2. Okay, 0.2. All right, and then your secondary voltage. Okay, your output voltage, you need to be very careful here. You need to look at your circuit. This is series. Okay, for those of you who already forget your series and parallel. All right, so in your series, your voltage is shared among the circuit. When it's parallel, the voltage is the same. All right, so since this is series, right, I need to add up the voltage here. So your secondary voltage here is 24 volts and not 12 volts. All right, and then multiply to your current. Okay, so you need to be careful of the circuit that they are using. Look carefully whether it's about series or parallel. All right, if it's series, it's about series and parallel. You need to remember the relationship here. Okay, so your secondary current here, if you were to calculate 240, 24, is it 2? Yeah. Okay, so current here is 2 ampere, right? Just to show you this one, the important thing here. Okay, all right, efficiency, blah, 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 blah. Okay, transformer is used to lower the electrical supply. Okay, so you have a power rating of, not power rating, rated 12V and 2A. If the current in the primary coil is 0, blah, 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 what is the efficiency? So efficiency is power output divided by power input times 100%, right? Okay, so I can change this formula into like this: Vp IV. Oh, sorry, Vs Is. What is output? Output at the top. So Vs Is, secondary voltage, input voltage, output voltage, secondary voltage, and also current. Okay, confusing. All right. So let's check. So supply 240. So to calculate my efficiency. Oh my god. Okay, never mind. If you want to calculate separately, also can. Meaning you calculate P equals to VI for output, and then P equals to VI for input, and then only you put into this formula also can. But I straight away use this straight put in everything. Okay, supply power rated, blah, blah, blah. So this is output. So 12 times 2 divided by, if the current in the primary, so this is primary, so 240 times is 0.15 100. Okay, so this one if you calculate, you 麻烦 troublesome. So you are going to get like 67%, 66.67%. Okay, that is the efficiency of the transformer. All right, meaning that of your power input here. Okay, your 240 watts here. If I were to calculate the power here, 240 times. Okay, this is 36 watts. Meaning of the 36 watts, only 66% is converted into output power. Alright, and the remaining one is released as heat. So this is not really efficient. Okay, alright, so you need to understand what you're doing here. Okay, done. Alright, let's look at another one. Transformer used to supply two 12V connected in parallel. So remember, if it's parallel, meaning you have the same voltage. Doesn't matter how many bulbs you have. Parallel, the voltage is the same. So remain as 12 volts. Okay, so the voltage of the electrical supply is 240 volts and the efficiency is 96%. Okay, so first we calculate the number of turns in the secondary coil. Alright, so we use the formula. Okay, so your secondary output voltage is 12 volts. Okay, it's not 24 because this is parallel. Alright, input is 240. I don't know. Primary is 900. Now, if you notice, right, just now in the upper one, I'm using VP over VS. Now I'm using VS over VP. It doesn't matter where you put on top, where you put bottom, as long as you put it correctly. Meaning that I can also put it like this. But the other side must also be the same. Okay, so it doesn't matter the arrangement up or down as long as you put it correct. Meaning you don't put VP here and then here you put NS, then that one is definitely wrong. Alright, okay. So my secondary coil here, the number of my secondary coil here will be 12 times 45 turns. Okay, alright. Next one, calculate the current in the primary coil so that the bulb is lit normally. Okay, so for the second one, since they already tell me the efficiency, right? So I know I need to use the efficiency formula. Okay, so efficiency. Alright, output, power output, power input. Okay, now let me just put it right here. Okay, so my output power. Okay, in this case, right? Since they already tell me the power rating of the light bulb, and I have two light bulbs. Now, for power, right, we don't need to know whether it's series or parallel. Okay, for power, if it's 2, we just add up the total watts here. So 2 light bulbs, meaning my output power here on top, I can straight away put in is 48. Alright, and then they want me to calculate the current in the primary coil, right? So my input power is 240 times primary coil current, because I don't know the current in my primary coil. Okay, then times 100%. So efficiency given here is 96. Alright, so basically we just rearrange the formula. Okay, the bottom part here I'm using the VI formula, voltage times current, because it's power. Because I want to find the current here. Alright, so this one we just rearrange your formula and then, okay, I'll calculate a bit long, let me just see. Okay, this is 0.21 ampere. Alright, let me double confirm. Okay, so divide by 240. Yeah, correct. This is 0.21 ampere. Alright, so that is how you use your efficiency formula. Okay, just remember, just look at the question what they want. If you see efficiency, meaning you need to apply this. If you see ideal transformer, meaning is VP VIP equals to VSIS. Okay, it's very simple actually. Alright, okay, last one, let's look at this one. Transformer in the diagram, brightness. Okay, remember, a transformer can only work with the alternating current. If I change this into a battery, right, meaning the transformer will not light up. Okay, just remember that. Okay, let me see if there are any more difficult questions for us to look at. Okay, this one, question number 12. Efficiency 90%, meaning I need to use the efficiency formula. Alright, power dissipated. Okay, if you see the word power dissipated, right, meaning that the what they call formula that we normally use is the V square over R formula. Okay, so if I want to calculate the power dissipated, alright, it's either this or this. I square R. Okay, because if I were to put in V equals to IR into this formula here, it will become I squared and R squared over R. If you cancel off, you will get I squared R. That is how we get this thing. Alright, okay, just know that for power dissipated, okay, power dissipated, we use this formula. Okay, I squared R. Alright, so okay, now this one, right, joules per second is the same as watts. Okay, so they want me to calculate the voltage across the resistor. Alright, so this one, since they want the voltage, right, meaning I'm going to use this V square R. Okay, so power here is this one, 4.5 watts. V square over the resistance, this is 2 ohm. Okay, so V square equals to 9. So V is equals to 3 volts, square root lah. Alright, okay. Next, they want to know the current, okay, flowing in the primary coil. Alright, so they let me know the efficiency, right? Oops. Okay, so efficiency. Okay, meaning that output VSIS over VPIP times 100%. Alright, in this case, the output I already know, right, is 45, not 45, 4.5. So this one, the top here, I straight away put in is 4.5. Alright, VP, okay, input is 240. I don't know my, I did want to know the, what they call IP lah. So this is 90%. Okay, so we just calculate. So 90 divided 100, oopsie, 0.9. 4.5 divided 0.9, 5 divided 240. The current here will be 0.02 amperes. Okay, hopefully I didn't calculate wrong. Alright, okay, just to show you the steps on how we calculate lah. Alright, so that is how we use the formulas. Okay, alright, okay, hopefully that is enough lah. Really many examples. Alright, okay, in this part I'm not going to go into all these things. You need to know what they call the different types of designs of your power plants. Right, just remember that all power plants, right, they are generating alternating current. Okay, so the power that goes into a house is actually alternating current. So you need to know all the different types of power plants, how they produce the energy, alright, so on and so forth. Okay, their effects, the pollution, all those things they will ask lah. Alright. Okay, so energy transmission, or what we call as the national grid network. Okay, meaning this one. Okay, so you need to roughly know how your national grid networks function or works. So I'm going to explain very briefly here. Right, so you have your power plant. Okay, a power plant generates roughly around 33 kilovolts. Now, before they send this to your house, they need to up the voltage first. Okay, so to up voltage, that's why the first part here we are going to use step up transformer. Alright, so maybe in the exam they will ask you to calculate the number of coils here, okay, for the step up transformer. Alright, but we need to step up until 400 kilovolts. Why do we need to step up into 400 kilovolts? Is that in order to send your power or your electricity, right, it's very far away. Remember when we talk about voltage, right, it's about energy. If you send it at low energy, right, maybe the power or your current, right, go halfway, it won't even reach your house, already lost as don't know what already, heat energy all gone. So maybe not enough power lah, in other words. Okay, so in order to make sure that all the electricity can be sent to your house more efficiently, right, what they will do is they will up the voltage, meaning I give them very high energy so that they can travel very far away. So it makes sense, right? If you take car, you want to travel until Penang, you need to make sure that you have enough petrol, then only you can reach Penang. Alright, if not halfway, then you stop. Okay, so roughly the same concept applies here lah. Alright, in order to send your electrical energy or electricity, I need to give them high energy. Make sure they have enough energy to reach your house. If not, later halfway stop, then gone. Okay, so they are going to up first, and then only they send. So when they send, right, slowly they will step down according to what they require. Alright, so heavy industries normally will require 33 kilovolts. Okay, so when they reach the heavy industry here, right, they will have a transformer step down. Okay, light industry step down, and then buildings around 450. This one is like your hospitals or your offices. The current or the voltage that goes in is around 450 volts. All right, and then when you reach your house, it's 240 volts. So just remember, starting point we up, and then after that it's all down. Okay, the reason why we up is we want to make sure that your voltage is high enough, okay, to overcome the resistance so that it can be sent to your house. All right, so I just briefly explain for you lah. Of course, you need to know the what they call the cable, the type of cables that you need to use. Should you use a high resistance or low resistance cable? All right, all those things are very factual stuff, so I'm not going to go into too technical about it. All right, I'm just going to go into the calculation part. Okay, calculations involving the what they call electricity or your national grid network lah. Alright, for example like this. Okay, a 50 kilowatt electrical generator. Okay, so two formulas that I'm going to use is this one. First one is this, I square R. Okay, second one is P equals to VI. Now, what is the function of this one? This formula is to calculate energy loss or power loss or power dissipated, okay, in the cable. Alright, this is to allow me to calculate the current in the cable. Okay, in other words, you actually need to use this formula to first calculate the current in the cable, then only you can apply into this formula. Alright, so a lot of students, they always use the wrong values to substitute in, or they don't even know when you need to use this, when you need to use this. Okay, so let me just show you an example. Alright, 50 kilowatt electrical generator is connected to a factory, okay, by a cable with a total resistance of 5 ohm. So I just draw out lah, generator, and then factory. Woohoo! Don't know what factory is this. So here is 50 kilowatts. Alright, and then the factory, the cable resistance here is 5 ohm. Alright, this is your electrical cable lah. Okay, if the transmission voltage is 5000 volts, what is the current in the cable? Alright, so to calculate the current in the cable, I need to use this formula, P equals to VI. Right, so your power here is 50 kilowatts, okay, meaning from the generator, right? So I need to change off the kilo, so 50,000 watts. Voltage is 5,000, okay, and then your current. So this one will be 10 amperes. Alright, and then second, they ask me what is the maximum power received by the factory. Now, when the power is transmitted in the cable, some will be released as heat, meaning some of the 50 kilowatts power, right, will be dissipated as heat energy, meaning not all 50 kilowatts will reach your factory. So we need to calculate the power loss. Okay, then only we can know how much power is received by the factory. So to calculate the power loss, we are going to use this formula, P equals to I square R. Alright, so the I here is the one in the cable, the current in the cable from this value here. So it's 10 squared multiplied to the resistance here, which is 5. So this one will be 500 watts. Okay, in other words, of the 50 kilowatts, 500 watt is being released as heat. So 500 hilang. So the only remaining left that reaches the factory is, so I write here lah, power received. How do I even spell receive? Okay, never mind. What am I doing? Alright, power received is the initial 50,000 watts minus the one that is lost, 500. Okay, so you have 45,000 watts or 45 kilowatts lah basically. Sorry, what 45 kilowatt pula? 49,000. 49,500 watts. Okay, correct. 500. Okay, correct. Alright, so this is your power received by the factory. So just remember, alright, This formula is to calculate power loss. So if you transmit energy through your electrical cable, right, definitely will have power loss. So we need to calculate. But in order to use this formula, I need to know the current in the cable. So this value here comes from this formula, current in the cable. Okay, so make sure you use the correct value. All right. Let me show you another one. Another one. A small power station supplies, okay, 1000 at the voltage of 66 kilovolts to a factory. Okay, same thing. Transmission cable has a resistance of 40 ohm. Current in the cable, so P equals to VI. Okay, 1650000. Okay, we need to change the prefix. Then I. So your current here will be, let me just look at this one. How much is this? 25 ampere. Okay, let me just check. Okay, correct. 25 ampere. So this is the current in the cable. And then energy loss in the cable, meaning I use this one, I square R. So we use the value here. 25. Resistance is 40 ohm, right? So this one will give me 25,000 watts. Okay, this is the power loss, power hilang. Alright, so transmission efficiency. Okay, transmission efficiency. Okay, meaning I need to know my output power and my input power 100%. Now, this is not your output power. This is energy loss. Okay, so your output power you need to minus off. You take the original one. Okay, 1650000. Okay, minus energy loss. Alright, 1650000. So many zeros. So this is your output power. Okay, so this is the value that you should use. Okay, so you need to understand this is not output power, this is energy loss. Output power, I need to take the initial one minus off the one that is hilang, that is lost, then only I can get the output power. Then only we calculate the efficiency. So output power 1625 000 divided by initially is 1650 times 100%. So this one will give us okay, around 98% efficiency. So this is rather high efficiency. Okay, all right, meaning that the what they call the transmission of this cable is very good because 98% is converted into useful output power. All right, so basically that is it. Woo-hoo. Okay, calculations involving all your transformer things lah. All right, so hopefully this one clarifies a little bit lah. Okay, because I know that a lot of students have problems applying formula. You know the formula, but you don't know when to apply the formula. Okay, so just remember this one. All right, especially for the transmission of electricity. Okay, this is energy loss or power dissipated. Okay, this one is to calculate the current in the cable. All right, and then if it's about efficiency, you need to calculate your output and then divide it by your input. All right, so that is it. Okay, done. All right, next part will be about your transistors. Okay, I'll see you in the next video. Bye bye.